Okay, so I'm going to go over the problems for Codeforce round 898 Division 4, and of which I think um, I'll just go over. Okay, sorry, I'm just going to go over the problems, my solutions I came up with during the virtual contest. I did do a video of the virtual contest, but I feel like it's better just to go over the problems like this, and um, and also I'll probably look at the editorial because I haven't looked at the editorial yet, so I don't know what are the other solutions to the problem or there are other approaches. So the first one is shortstop is really just swapping two characters in a string that only has three characters. So you could just loop through that um, with two loops like this, and then just do simulate every swap and then check once it's equal to target because you just want to check if it's equal to ABC. This one, good kid, you want to increase the value of one of the elements in these arrays, which are the arrays contain just digits actually. They're just 1 to 9, and you want to increase the value of one of them, and it's best to increase the value of the smallest element and then just take the product of that. So the code is just like this, just you sort it, and then you can take the 0th element will be the smallest element, and you can increment by 1 and take the product of that. And the proof is this. So given an array of elements like this, you can order them, you sort them, right? And let's say this is your smallest element. You could define your smallest element as being x, and then everything else would be um, either equal to x or x plus some value, x plus 1, x plus 2, right? So it could be something like this. And then if you were to increase, like let's take the two extremes. Suppose you were to increase the the largest element by 1. If you did that, this x plus 2 become x plus 3, which is basically the same thing as if you distribute, if you say all of this, all the prefix product of all these values is x1, so x, and you take x1 and you take x1 times, I guess I didn't write x1 over here, you take x1 times this, you're really just taking, the original was this 2, right? So this 3 is just really just adding x1. So you're just incrementing x1 to the product. That is, if you say the product of everything um, is equal to this, then what you're doing is by taking these, you're saying you're taking the total product and you're increasing it by x1. Okay. But let's suppose you increase the first element. If you do that, then you could say this is your product, and you're basically going to be adding this to x you're going to be adding this to your x. So you'll be, instead of doing that, you'll be doing x plus x2, which is better because this suffix product is going to be larger than this prefix product because it contains larger elements. So the total product is be greater. Um, so if this product is greater, it's better to pick that one than it is to pick the other one. So that means it is always better to to increase the last element by 1. Um, okay, and problem C is target practice. So you have this target with 5 rings, and each ring has different point values. So the outermost ring is point value 1, 2, 3, 4, 5. So the solution that I did was I just did a breadth first search, starting from all the border cells and giving them a value of 1, and then incrementing the value as it goes into the rings. And whenever it sees an X, it increments by that. So the code is just this grid. So it just gets all the elements on the border, it builds it into the deck, and then it goes through the deck and increments the depth. The max depth will be 5. So and then it increase the res corresponding to that depth that was found. But I think there's another way to do it. I haven't actually done this yet. Okay, let's suppose you have an RC that's here, right? So if you're let's suppose you're here. If you're here, then what's your distance to the border, right? You can calculate it. You can say R is your distance. So R is your distance from up here. And you could say C is your distance from over here, right? This is a bad way of writing it. Let's say this. Let's say this is R, and let's say this is C. but you could be also have come from over here, so you need this. Well, this would be C minus C, like this is a uppercase C. Um, and then this one would be from down here. So this one would be uppercase R minus R. Um, yeah. And basically you just take the min of those. So you take the min of those four values. So R, C, and I'm just trying to think because R is going to be 1 here, right? It's going to be 1. And then R minus R and C minus C. So you just take the min of that and that would be your value. If we zero index everything, then, then like let's say, because R is going to be 10, so if you take 10 minus 0, you're going to get 10. Let's say you're all the way down here, so you're in the ninth cell. If you're in this cell down here in the ninth one, and you take 10 minus 9, you're going to get 1. So I think you need to subtract 1 from these. Okay. And then the value would just be, okay, so the value you want to add would be v plus 1 though. Okay, so this is another alternative solution. Let's implement it because it's going to be fun. I'm just going to set n equals a 10 since it's a square grid. Sorry, this is typo. Okay. So if it is, you want to do res plus or equal the min of plus 1. And boom. That's your answer. This is so much cleaner. I mean, when I was doing the contest, I thought there was probably a solution that was like this, but I was like, there's probably a math pattern or a pattern you could use, and you could just do math like this, take the min. But I was like, doing the contest, the virtual contest, I guess. I didn't do the actual contest. I was just like, wait, can I submit this? This is a solution I was looking at earlier. But during the contest, I was just like, I was like, I don't think, I feel like I should just go with what I know will work without something that I didn't have to like prove or anything. Which in this case, I feel like the proof was just so easy that maybe I should have done that. And writing the code would have been quicker. Um, but okay, let's move on to D. So 1D eraser. So you're given a strip of paper S that's in cells long. Each cell is either black or white. Okay, so for this problem, it's like you take like a fixed length sliding window idea, because it says you can change all the cells in k consecutive cells to all. You can change them all to white, but it's like the algorithm is you want to take a fixed size window of size k, but you want to start the operation whenever black is in the leftmost of the window. So so like so basically, if you have any type of like if you have some elements W black black W, let's say K is 3. Um, if you change all of these to white, um, hold on. Wait, hold on. No, make this. Oh no, this is bad. Let me make this a W here. W here and B here. So okay, yeah. So if you make this all white and then you make this all white, let's make that, or this all white, then you could end up having to use too many operations. So the best thing to do is to start it as late as possible. So that is, take your window here and perform the operation here, transform all of these to whites, and then you just have to do it here. It doesn't really matter that it doesn't continue here, but in this case, you greedily are choosing the smallest number of operations, the smallest number of windows that you need, because you're having B all the way at the leftmost, right? Like it doesn't make sense to do this as your window. It only makes sense to have your window contain B at the beginning as the first element, and then the other elements don't really matter. And then you just have to do the operation there, um, and then you just have to move it on. So the code looks like this. So basically, you create your point, you create your left and your res, and then if it's a W, okay, just continue. It doesn't matter. Um, Otherwise, you increase res by 1 because that means it means you hit a black cell, um, and you're gonna have to now begin the process. And basically, what you do is you just do left plus K. You say, okay, well, in one operation, I can change everything at this cell to white, and also everything as K larger or up to N, and then just go through there and then set left to right. That is, you can skip ahead now. You don't have to. Um, you can skip K steps for the next one. Mm, so that's that problem. I think that was pretty straightforward. For this problem, what was I gonna say? No, actually, I'm just going on. Okay, so this one's E, building an aquarium. Okay, this one is you want to figure out the height of the tank, and the tank can be like here they're choosing the height to be 4, and so now it's saying how much water will be filled in the tank. And basically, you can figure out the water based on by taking the height minus the A values. So like 4 minus 3 is 1, 4 minus 1 is 3, 4 minus 2 is 2, etc. If it goes above the height of the tank, then it's not going to be filled with any water, but you're just filling this tank in up to this water height. So and then this visual kind of really explains it. But basically, what you can do is you need to find h. Well, h can be many values because you can use up to 1 billion units of water to fill the tank. So h can be really large. So really, what you want to do is you want to binary search on h and then perform an algorithm, and then you just want to loop through and check that you don't use more water uh, than you're given in the problem. So this is my solution. So basically, it does binary search, sets the left and right pointers, and then it takes the sum, and then I do the mid, which is like, so mid is the current height it's proposing, and it's doing that minus a for each a in the array. Do 0 because like if a is larger than mid, it's going to be negative, or if it's equal, it's going to be 0, and you just want to add 0 for those. And you just have to check that you're using less than or equal to the units of water available. If so, you can do true up to that point, and you can just skip now all those elements. Everything in the left element you know is going to be true now, so you're going to continue just lurking in the right segment. So you just, binary search is just, you have a segment, splits it in half, and then does a search on each segment. So this is just implementation for that. I'm not going to go over binary search that much since it's just kind of a big not a topic not for this video. But okay, but here, this is a mistake I made. I did like 10 to the 9, but I should probably always go a little larger. For some reason, I thought the largest it could be is 10 to the 9, but I still don't know why it has to be larger than 10 to the 9. Guess I would have to look at this, but I'd have to think about that. Like, for some reason, I thought the worst case was if you have 1 and then it's A1, and then you have like 10 to the 9 units of water. Like I thought that would be the largest height, because then the height would be, I guess 10. Oh no, the largest height actually would be if these are all 10 to the 9. Yeah, actually the largest, if this is 10 to the 9 and you have 10 to the 9 here, then the height could be, I guess, 10 to the 9 uh plus 10 to the 9. Yeah, so 10 to the 10 would have worked. It's 10 to the 9 plus 10 to the 9. That's okay. I see where my mistake was. So the largest would have been 10 to the 9 plus 10 to the 9, or 2 times 10 to the 9. Okay. And this the problem F is money trees. This is where I think it gets. But anyways, basic problem for this one, and I remember I messed this one up because I mixed up which ones were height and values. Yeah, so height is actually your second array. Values, the fruits are the first array. But for this one, it just says you want to choose a continuous subarray of the array such that each case that basically the next element in the height array, or hi, is divisible by the next element in the height array, which is the same thing as just saying like the modulus of hi with hi plus 1 is equal to 0. There's the remainder is 0. There's no remainder. You'll collect all the trees in that subarray, and so you just sum up the fruits in those in that tree. But if you collect more than k fruits in total, you're gonna get caught. So you just want to find the maximum length of a subarray given this, and if I recall, it's yeah, and that was right. That's another mistake that I made, is that you this height parameter allows you to produce like a window, in a sense. That is, you go to the left and then you say how much right can I go before it no longer satisfies this divisibility constraint. And once you do that, then what you need to do is you actually need to find the largest subarray within that window, right? So you already have a window. Now you just want to find the largest subarray in that window that follows the constraint where it doesn't ever exceed k. So then you do a sliding window algorithm on that. It's kind of like a sliding window inside a sliding window, I guess you could say. And then you skip left to the right. So um, I think this problem is actually interesting, but also um, one of the easier type problems. So here's what I'm saying. So like, let's say this is a subarray of L all the way to HR, right? Like, say these all satisfy that constraint, the divisibility constraint, and so you have all these. Now you want to choose your elements in here. Like choosing these elements, maybe you could choose this subarray and it'll be less than k. Okay, or maybe you could choose a subarray here and it's less than k. So like you want to pick that subarray in there that is the best, that's the longest, basically. So you can use like a sliding window for that. Okay, so the next problem, this is where it gets interesting for me. So this one's called ABC or BACB. So this problem is interesting. At first, I guess let me just go and describe it real quick. So it says you're given a string S made up of characters A and B. Initially, you have no coins. You can perform two types of operations. You can pick a substring AB and change it to BC and get a coin. You can pick a substring BA, change it to CB and get a coin. What is the most number of coins you can obtain? So in other words, you're just trying to find the maximum number of these operations you can do, because each operation gives you a coin. Each operation meaning that you change AB to BC or BA to CB. So you have those two type of transformations in the substring, and you want to find which one you can do the most um, in the substring or in the string. So the string is up to like 200,000. So like these are some examples. So like for instance, here AB, BA, you can transform the AB to BC, and you can transform the BA to the CB, and now you have no more transformations. Yeah, so this problem I think is very interesting. So at first I was thinking something like dynamic programming, and actually I think I did end up implementing like a dynamic programming, but also I ended up implementing dynamic programming, but also like greedy. Like I broke it down into two cases. So let me go over the strategy here. So the the first example is, let's say you have a B B A or something like this, right? But this two B's in here is actually very important. But what the reason I'm showing this is because when you have AB can get transformed into BC. So when you do that transformation, you're kind of actually just kind of like pushing the B out here. So that allows you then this is going to be an AB. So then you can also transform this to BC, right? So you have two transformations over here, and then you also have two transformations over here. That is, this BA can become CB, and then this will be a BA, and it becomes CB. So you have like two operations on both. But whenever you do it, so like at the end, once you do it, you're going to end up getting this as your string, right? Okay, well that's cool. But now this is where it kind of like tricked me up, and I was like, uh-oh, what do I do? What do I have to do in this situation? Let's say you have something like this. Now, this is very important that you have just one B. This you had two B's, but you could imagine this with any number of B's. When you have one B, when you transform it into BC, or sorry, if you transform over here, it's going to transform to CB. So this C won't work with these A's. So if you choose to go this route, you can only get these three. But if you choose to go the other route and convert AB to BC, then you can't go this route, but you can continue going this route. So how I saw it was you can get 2 or 3 with a B like this. So I had like two cases. Like I had cases where the A is partitioned by these, or can be split by these B's where there's only like a single B element, or it can be partitioned by like multiple B's. And then what another thing that you can observe though for the multiple B case, so for this case, it actually breaks down to something really interesting. Because you can say another thing here. There's another case. So this one is an example you have when you have more A's than you do B's, right? So you have more A groups than you do B groups. So A groups, there's more A groups than B groups, and exactly by one actually. Or you could imagine that this is an example where it starts with an A, and then within this it has like it has A, and then it has like a single B, and then you could have another single B, an unlimited number, but also then ends with an A, right? It ends with an A group. So each of these A's could represent like a whole group. Like it doesn't matter. I don't need to represent it like this. I could just say this. There's a group of A's here. There's a group of A's here, and then these are singular B's. I guess I'll just mark it by B1, so that I know it's singular. So this is kind of what this group looked like. But okay, you could have had something like this. Yeah, well, this is the same thing, right? Well, this is actually different. It's slightly different. It's different in the way that now this B can collect these A's, and then this B can transform these A's. So now you can do both transformations. You don't have to pick 2 or 3. You get 2 and 2. So it's kind of different. So basically, the conclusion here is if you have a group where it starts with a B1 and then it goes to another B1, then it goes to an A group, uh, which can have multiple A's, and then it goes to another B1, it goes to another A group, another B1, whatever, so on and so on, and it ends with an A group. You basically could say, okay, well, what's happening here is you start with a B1, and then it goes all the way through and ends with an A group. So you could have something like that, and then I guess like symmetry and whatnot, it's no different. That's not really any different from if you have this too. If you have the B1 on the starting at the end instead of starting at the beginning. So okay, so you have that type of group, and then you have the group up here that is represented by it starts with an A and ends with an A. And within here, it only contains singular B's. So the size of B groups is always 1 here. Okay, so that's a special edge case, but because let's take an example up here. When you have multiple B's, you can use this B to collect this A and this B to collect this A. So like you can imagine any example, like you say, oh, I have some A's. Okay, well I have some B's. I have some A's. I have some B's. I have some A's, and so on, right? Like, it doesn't matter what you do here because this B can collect all these A's, this B can transform all these, this B can transform all these too, this B can transform all these A's. So you can like, you can do the number of transformations you can do in this example is basically the count of A's, right? You just count out how many A's are there. And then the other observation that you can make is, um, or that we can make is that, um, is that basically, sorry. The other observation we can make is that you can go from, what is it? Okay, yeah. The other observation we can make is that you can go from, you can do this, right? Okay, well, what if there's a singular group? Like, let's say you have an A, B, B. Okay, there's multiple B's here, A. But then you have a singular group, A, you have B. Let's say you have a singular group over here too, and then you have A, etc., etc. So what's interesting is that these singular groups don't matter. If you have one group of B's where there's multiple B's, that guarantees that you can collect all the A's around it. And that means that these B groups are going to always represent something where like where like this B then can take everything over here. This B can take everything over here. So you can say if you remove all of these A groups, like all of these A groups that contain the multiple B's, if you remove all of these, then what you're left with is a group where it's going to be a single B and ends with an A. And it doesn't really matter what happens in here. They can all be single B's, which actually they will be. And then it starts with a B and ends with an A, but like you can use this B to collect everything over here, right? You can use this B to collect everything over here, and it doesn't matter if there's multiple B's. Like this segment here is actually supposed to represent this. You know, you have this, so you have multiple B's, but they're all singular because you removed all the ones that are double because you say all the double ones can take everything, so you remove all the A's around it. So you subtract off this. If you subtract off a group like this, you're gonna be left with a group that starts with a B and ends with an A, or it can end with a B. Doesn't actually matter. Um, or it starts with a B and ends with a B or an A, right? Okay, it doesn't really matter what it ends with, but if it ends with an A, you can still collect all the A's in these group, and then if for some reason you leave like a middle group could be like this, but like this one doesn't matter. You can still collect everything within here. So so yeah, so basically the solution is I'm gonna take a look at my code, I think, here, is that first off, if B is not an S, return 0. There's no solution. The B's have to be used for the transformation to occur. The other thing you check is if any key of B and any group of B is greater than 1, that is, it has two consecutive B's at any location in the string, then you return the count of A. That is, you can do transformation. The number of transformations you can make is equivalent to the number of A characters in the string. So that's like a simple case. So okay, once you do that, now the rest of the solution is for when when every single group B is of a single element. So it's more looking at this second case down here. And so the reason why you have to look at this one is because like you kind of have to choose, right? You have a choice here. It's either 2 or 3. Obviously 3 is better, but you can't make choices like this. To solve this, what I was thinking is you could use dynamic programming, because this is like a choice here. You're going to choose the element that's to the left of B, you're going to use the B to perform transformations to the left or to the right. And if you use dynamic programming, you can maybe track the ultimate best based off of subproblems. So for this problem, the subproblems was this. This is how I visualize it, at least. I don't know how uh, beneficial this is, but how I visualize it was this, is that each B is separated by, will have two components, a left side and a right side. Now these components are just A's. So these left and right components are just A's. It starts with A, ends with A's. It's just a group. It's just a group of A's. Um, so for each B, you're going to have these components, this left and this right, and then you have another B. But just but the thing is that, let's just say this: the left segment for this one is going to be the right of this B, and then it's going to have its own left segment. So my idea was this: is let's consider that I'm at this B right now. And let's consider the actions I want to take. So this is my subproblem. I'm at this B. And so for this subproblem, I want to update two options. I want to say, is it better that I take the elements to the, oh my God, yeah, to the left of it, right? These are going to be to the left of it. Or is it better that I take the elements to the right of it? Okay, well, we can look at how these transformations depend on the previous states. So if I were to take the elements from the left, so if I'm choosing left, I'm going to say left, call this B2, this is B1. So I say left of B2, although you don't have to do that, you can just say left is going to be, and then if you take the left element, you could take your previous left value and add this count to it, right? Because my left and right are just going to be like these dynamic programming values I'm storing. It's just saying for the previous B, this was the number of transformations if I took the segment to the left of it, and this number, the maximum of transformations if I take the segment to the right of it, in terms of the segment being the A segment. So the other thing I conceptualize is like an L count. This is the size of the left group and the size of the right group. So if I take the left group, that means I would have to have taken the left from the previous. So the current left, I don't know if this, let's call it new left, I guess. The new left is going to be equal to the previous left, right? If I'm taking the left of this one, then I must have taken the left of B1. So the previous left plus the L count, which is the size of taking the left of B2. And that's like the new left, right? But that's not your only option. You have another option. So this is a max, actually. Your other option is you don't take the left count, but you just take the previous right count. That is, it made more sense to have this be just take the right segment, and when you do that, you can't. And when you're choosing the left segment, you can't choose anything. If you're gonna have this be associated to the values on the left, you can't take anything. I feel like this is hard to explain. I'm not very good at explaining this one. I need to get better at explaining. That's also part of the point of doing these videos. But okay, so this would be a max of, now if you take the right segment, your previous states are, I mean, it's either left or right, right? It doesn't matter. Like this, if B1 took the left or the right, it doesn't matter because you can always take this one over here. It doesn't conflict. So you just want to take the max of left or right, whichever one was better, and then just add the right count. So these are your transformation states. There's some like edge cases though, because like if you start with a B and you have groups like this and you end with a B, you want to append a 0 here and just say this is, and you want to append a 0 at the end if there's a B element at the end. So basically just to say that the size of the A group is 0, that is, there is no A group. That way it will like appropriately do this calculation. And so this is the code for it. So you create this array, and like I said, if the first element is B, then you want to append a 0. You just want to say, well, okay, there's no A group here to the left of this B. And then you just go through the groups, and every time you get an A, you're going to append that size of that A group. and then at the end you're going to append a 0 if it ends with a B. Then you're going to store the left and the right value, so initialize them as 0, so that is that's if you take nothing, and then you're going to do I for n minus 1. So when you're at the current state, you're looking at the left and the right count. So this is considering the first B, and the first B, it has the left count is the number of A's to the left of it, and the right count is the number of A's, the size of the A group to the right of it. Like it's a group though, it's consecutive A's, not all the A's, of course. And then you just do the update, which is for the left side, you take the right, and then you take the left plus the left count. And for the right side, it was the left, right, plus right count. So just what we basically said. And then your answer is basically, the max of this. So this is my solution. I feel like I thought this was an interesting problem. I'm gonna guess that there is a simpler solution for this, so we'll take a look at that in the editorial in a minute, but that's what I was able to come up with. Okay, here we have Mad City. So for this problem, is a graph problem. This was also a really interesting problem. I feel like these two last problems were really were like were just good good problems, challenging problems that really kind of made you think. So for this one, you basically have an undirected graph, and it's not going to be a tree because you're given n edges. So so basically what happens here is during each move you have Valor. I don't know how to say these names that well, but Valeru and Marcel, and Marcel or Valeru can predict where Marcel will go in the next move. So Valeru knows where Marcel will go. And with this information, Valeru can choose his move. And then it just says some more information, blah, blah. And you basically just want to find if Valeru can indefinitely escape Marcel. The basic idea here is that Valeru can escape Marcel forever, given that he always knows where Marcel is going to move next, if Valeru is in a cycle on the graph. Because in a cycle on the graph, he can always move away from Marcel. There's always a way to move away from him. But the problem reduces to more than just that. It's not okay. If you're in a cycle, if Valeru's in a cycle, yeah, he can always escape from Marcel, unless of course they start at the same node. Like starting at the same node is kind of like an edge case. But the other thing is that if the other case is this though. What if Valeru is not in a cycle? If he's not in a cycle and Marcel's not in a cycle, then there's a chance that Valeru can get to the cycle before Marcel catches him, right? There's a chance, and there's some way to do that. The problem becomes more simple when you kind of like read into it because you know there's only gonna be one cycle. So basically, Valeru just has to beat Marcel to the cycle, and that's kind of like a shortest distance problem. So you can kind of see you're gonna be using a depth first search, a breadth first search. You can use a depth first search to find cycles really easily. But there's an even better solution, which I'll go over in a minute. Actually, I haven't written it out yet, but I've already seen it because I looked through some. I haven't looked through the editorial, but I was like wondering about how you could solve this. So this is my code in Python. So I'm going to go over the solution because like the code is just really long. But basically the code is I use a depth first search to find the cycles, and then it gets the shortest distance from A to the cycle, and then it has to find the shortest distance from, or this is the shortest distance for Valeru to a node in the cycle, how quickly he can get to the cycle to escape forever, and then this is calculates the distance of Marcel to get to where Valeru is, basically where Valeru can reach the cycle. And then you just basically say, oh, if he can reach it before him and so on. But then this code didn't work, so I had to rewrite it in C++, which is, so the problem took me like extra 30 minutes to just do this. But it's just really long. Python didn't work because like this is a recursive function, and sometimes I have trouble. I think I always have trouble with those in Codeforces. It's just There's not really any way around it. I tried these things, but they didn't work this time. Um, I don't really know what yeah, they do something. They're supposed to help, but they didn't. So like I just had to rewrite in C++ and then submit it, which took a long time because this is just like a lot of code here and I don't type that fast. But but basically, this is like one solution. So what I'm going to do is I'm coming with a simple solution. There is a solution you can do in Python. There's a solution where you don't even need to do this recursive depth first search. Um, and and the reason for that is because there's only one cycle. It just kind of the problem simplifies because of the graph. So let's just look at the basic cases though. So why is it that this is a cycle? So this is one of the graphs. So that's one thing about this graph. You're given n edges for n nodes. So that means a tree would have n minus one edges. So like this is a tree, but this has n minus one edges. So it has to have one more edge. And you're never given multi-direct edges, so only edges this one. So what you can kind of figure out is if you have just one extra edge, that basically means that you're always going to have one cycle in in the graph. But the cycle could be like, it could be like this, right? This is an example. Um, and it's an undirected graph and so on. But basically, there's always going to be just one cycle. But basically, let's say Valoroo, I'm going to say, I think they use A and B. So I think A is, which one is A? A is, B is, I think B is Valoroo. And I think A is Marcel. I'm trying to use the same ones that the variables they use. Say A, B. Yeah, Marcel is A and B is Valoroo. So Marcel's trying to catch B. Okay, so if B is in here and A is here, this is an example when Valoroo is in a cycle. In this case, he can escape because he knows where A is going to move. If A goes here, he's just going to go here. If A goes here, I mean, B could just choose not to move, or he can move, but he can always be one step ahead of A, no matter what. The other case is when they're not in the cycle, let's say. So let's say it's like this, and let's say A is here and B is here. So in this case, B can always be one step ahead, and he can make it to this cycle node here. And now he's in the cycle, so he can always escape. But if B was here, then there's no way that B can make it to the cycle before A. Like A will go here, and then he can get him. Um, and A will always kind of like go. So like if B, basically the distance from B to its nearest node that's within the cycle is the same distance as A to that. So basically you need to find this cycle node that is closest to B, and then you need to find out how the distance from A to that node. So in other words, I'm gonna draw another graph and like do colors on it. Let's do to represent this. And so like in any type of graph, really, you can always like this is some arbitrary graph. So in any type of graph, you can always detect a cycle by using depth first search and using like the two color. I think it's called a two colors algorithm or something. So you just like you do two colors, and that's what I did. So like um, that's what I did here, and you can do that for detecting this cycle. I'm not going to go into that, but there is an easier solution for this one that I'm gonna implement right now. And then, but basically, what you could do is you could say, let's say, let's say let's say B is here. So this is B, and let's say A is maybe, uh, let's say A is here. So this is A. Okay, so what's the closest node that's within this cycle for B to escape to? It's actually right here. Now, what we can do is we can say the shortest distance here and the shortest distance here, we're going to define this as dB, and we define this as dA. And we just say if dB is less than dA, then basically he can escape. So that means Valeru can escape to the cycle before A beats him to it. Um, and so I think that's all you have to really do. And like if A and B are in the same spot, that'll work. If so on so on. So now let's go into an algorithm that you can use for detecting the cycle in this type of problem. So if you do a degree count around each node, this will have a degree count of 1, 2, 2, 3, 2, 3, 1, 1, 3, 3, 2, 1. Um, so what's important here is that each of these nodes are part of the cycle, but also have like a tree, I guess you could say, attached to it. Each of these like critical points are gonna have a degree of 3. Could have a degree even greater than 3, but it's gonna have a degree 3 or greater. Like that would make it 4 if you had that. And then every node that's like not part of a cycle will have a degree of 2. And also nodes part of the cycle will have a degree of 2, but like these are like the nodes that are don't have like a tree attached to it, I guess you could say. You could treat these as trees. So all you have to do is do a topological sort basically. You start from all the ones and and you say and then you go do a topological sort. Then you're gonna go to the two. The two will decrease to a one. The two will decrease to a one. Now you decrease the three to a two and you decrease this three to a two. So the basic idea is that if it's not a 1, you don't search on there. So then you search on these, and then this one you convert to a 1, and you convert this one to a 2. And so basically, you're going to be able to search all of these nodes in the topological sort, this node, and then these nodes. But it won't search any node in the cycle because it's only searching nodes when their degree is equal to 1. That's being treated. These ones, when it enters, it's always going to be a degree of 2 because it's part of a cycle, there's these other two edges that were not yet traversed, and you're only able to traverse this edge coming in. Um, so it means there's no other like unexplored edge for that node. So if you do this, basically you can just everything, and then what you could do is for these ones, you say when it's done exploring, you can just set it to 0, and then you can just say everything where the count is not 0 is basically a node that's in the cycle. And if you do that, you don't need to use a depth first search to detect the cycle. So let's implement that solution real quick because that one I could do in Python. But this problem also kind of like taught me like, hey, you should probably use C++. C++ is better. Um, like here, see, I was implementing C++, boom, done. Same code, actually, same algorithm. It just doesn't work in Python. Um, and you can see like, all the ones run pretty fast, and it runs really fast too. Actually, did I make a target practice? Oh yeah. So let's implement this one real quick. Okay, so all we're gonna do is keep a degrees count. Okay, you won't need to do this. Instead, what it'll do is it will uh, set equal to 0. This is basically so you know it's not a cycle node, and pin it to your DQ. Yeah, okay. And then you can say do that. Can you do that? I guess you could do that. I think this will work. I don't think it really matters where you set this to 0. So, but you want to set it to 0 and then you just say like this one's done exploring. If the degrees is, I guess just do continue here. Otherwise, do this. And if it's equal to 1, then you want to look at that one next. So all the degrees that are basically not greater than 0 are part of the cycle. So then what you want to do is you want to find uh, you want to find you want to do this. You want to say start node, but your start node would be B, and then C, and you say while DQ. Okay, so if I think I need to check if visited here. Yes, it works. It's not super fast, but okay. That's cool that you can do it that way. Huh. So like, so basically, I used the degrees to figure out which ones are like still part of the cycle. Use like a topological sort, like a weird topological sort where you don't start from zeros, you start from the ones. I guess that makes sense. And you just go through it. Um, and then basically all the nodes in this cycle will still have a degrees greater than zero. Because I said the degree equals zero. I guess do you have to set the degree equals zero? I guess you don't. I feel like you don't have to do this. But like, I guess you would do that because you don't want to explore the node multiple times, maybe. Like, let's say you had, let's see, what if you had like this? Wait, how do I do this? Yeah, what if you had this or something like that? So let's say you go from here, here, here. It could be possible that you end up at these two at the same time. So then this one goes here, and then this one would go here. That could happen. So I think when you like, you should, I don't know why I didn't fail, but I feel like if this is true, you should set degrees v equals 0 right away. Yeah. All right, I think this makes more sense. Uh, Anyways, then you create this. Then you do. You're gonna start doing the breadth first search. What's interesting is this is actually breadth first. So you're just using breadth first search at this point. Um, then you do like a more traditional breadth first search. Just find the shortest distance, keep the distance, and keep the current element. Keep a visit array. Go through it. If the degrees is greater than 0, that means it is in the cycle. So you want to say this is the distance to B to the cycle node, and then this is like you just update B to the cycle node, like say, oh, B's at the cycle node now, and this is just going through. So then do another breadth first search from A, and then have A go until it meets the node where B is currently sitting, and find the distance of A to that node. And this will find out, and then just it's yes if distance B is less than this, and no otherwise. Okay, so that should work. Okay, so yeah, so that's an interesting problem. So the other thing I said I was going to do is go over the editorial. Um, let's see. Okay, let's take a look at the editorial. See if there's anything like. Okay, I'm not. These I feel like I should skip. Uh, yeah, they brute force it. Okay, and then it has this one. Target practice. Oh, they just hard coded it. I guess my solution is gonna be more than what they're expecting. Okay. Oh, true, 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 true. I didn't think of that. Okay, there's an optimization to this one. You don't need to actually go through and set them to white. You just have to do this, right? Like, there's no reason to actually like physically change the value of the cell. Okay. Right, there's not actually a reason to do that. It's just you have to skip now everything. So that should work for D. Okay. For aquarium, maximum height with a certain upper bound. Yes. Yep. 2 times AI plus epsilon. I knew that was the starting bound. But like, yeah. I mean, yeah, it doesn't really matter. This one. Oh, what? Oh, this is a different approach than what I did for money trees. But my approach is linear. So I don't know, like, this is a good approach. Maybe better, because this would be O of n and then O of n in here, so that's still O of n. Well, this isn't like O of n, my bad, sorry. This like skips all those elements and then processes them. Um, so I don't know, but what's their solution? They're do a binary search on the sizes segment. Okay, I see. I see, and they use a prefix sum to check if it's. Yeah, I see what they're doing. I see. So like, just trying to think. So you have each segment, and then it does it for each of the n operations, and then you can find uh, the maximum R that satisfies the height divisibility condition, and then you could binary search on that segment. I want to look at that code. So basically, yeah. I see. Okay. It's previous one plus one. Okay, yeah, so you just pre-compute them. Then you do the binary search here. Okay. And then this one. B is next to an A, eats and covers it. That's kind of how I was thinking of it too. Um, hmm. Oh, darn. I knew there was a simpler solution. It was like poking right at me too. But I mean, my dynamic programming solution works and it should like always work, but that's true. Okay. Okay. Let's go. I'm gonna read this one and I'll get back to that. Because they were true with an additional edge, graph has exactly one cycle. Oh, I guess, yeah, you could have started depth of first from Valeru's node, and then you could find the node where Valeru enters a cycle. So he has to be able to reach this node before Marcel can. True. So you could just use a depth first search and find like the first node where value root enters a cycle, and then you have to find if he can reach before my cell. I'm just looking at how they did it. So they find the entry node. Okay. Oh, then you find a distance value. I mean, okay. Let's think about this. You're still using three depth first search, and this approach uses three breadth first searches, which is just because it's easier to do that with Python. Um, yeah, but I mean, obviously I could have done this with depth first search. That's kind of what they're doing. But the only difference is that I'm like finding the entry node and the distance at the same time. I guess if I do it finding the distance, I could do it with like two functions. I guess there's a way to do this where you have like you can reuse code. Like I could have just had two breadth first search is um something like that. No, I would have had to use a depth first search for this solution. Okay, so what did I learn about this one? Here's what I learned. Oh no, darn it. Crap. Ugh. Okay, what am I doing? You need to find the number of groups there are, right? So like you need to find each A group and each B group. Yeah, so say B groups and say AG and BG. I just feel like Okay, this is a better solution. Cool. Just thinking about this. It makes sense too because um, it's just saying that. I think that's it though. I guess I could go into this problem a little more. I'm not gonna do it on this video, but or maybe I should. But then I think this one's too long already. Um, but yeah, I kind of get the. I'm gonna probably prove it to myself right now. Um, why it works, this approach. I mean, I think I already kind of get the idea based on this, because like what I did up here, like when it had multiple B's and it has A's, you can always it can always eat all the A's, right? If you have like singular B's, but the number of B's is same as the length, then you can eat all the A's. The the only time when you have fewer B groups or fewer B's than there are A groups is an example where like you start with a B and you end with the A, and each of the B groups is size one. And in that case, each B group can only like you can't cover all the A groups. There's one A group you can't cover. It makes sense to let that be the smallest A group. Right? I said I wasn't gonna prove it, but here I am. Like, let's say you have an A group over here, then you have the B A B A B A B A B A and so on. And we're saying that this is where we have 1, 2, 3, 4, 5, 6. We have six A groups, and we have 1, 2, 3, 4, 5 B's. So that's when it's less than six. It's one less. So each of the B's can cover one A's. So you just choose which A you don't want to cover. Like let's say this is your smallest A. So say okay, don't cover this A. Fine. Boom. You can have this B cover this B cover this one, and you're done. So you just subtract the smallest one. Actually, that is the proof, but yeah, I mean informal proof probably. All right. I think that's it though. So yep. Thank you for watching.